All right, so example 6. Example 6 is asking us to prove by induction that the sum from r is equal to 1 to n of 1 over r into r plus 1 is equal to n over n plus 1. So this is how it would start. So Pn is this initial statement that we're asked to prove. And that this is equal to n over n plus 1. I'm going to say when n is equal to 1, so on the left-hand side, I would have 1 over 1 into 1 plus 1. And on the right, I have 1 over 1 plus 1. All right, so over here, I have 1 over 1 times 2, which is a half. And over here, I have 1 over 2. So we can clearly see that Pn is true for n is equal to 1. We're to assume that Pk, which is the sum from r is equal to 1 to k of 1 over r into r plus 1, we're assuming that this is equal to k over k plus 1. We're to assume that this statement is true. Then we'd be required to prove that Pk plus 1, which is the sum from r is equal to 1 to k plus 1 of 1 over r into r plus 1 is equal to k plus 1 over k plus 1 plus 1, which would be equal to k plus 1 over k plus 2. All right, so we're required to prove this statement. So let's change the color ink for that last bit of it. So for starters, P k plus 1, which is the statement from r is equal to 1 to k plus 1 of 1 over r into r plus 1, is actually equal to Pk plus the k plus 1 term. Now, Pk from this line is assumed to be k plus 1. Now, plus the k plus 1 term, using the general term, it will be 1 over k plus 1, k plus 1 plus 1. So what we have here is k over k plus 1 plus 1 over k plus 1, k plus 2. So we need to find the LCM. The LCM is k plus 1, k plus 2. Now, k plus 1 into all of this is k plus 2 times k. So it's k times k plus 2 plus 1. Now, simplifying the numerator, this would be equal to k squared plus 2k plus 1 over k plus 1, k plus 2. If we factorize the numerator, we're going to get k plus 1 squared over k plus 1, k plus 2. So k plus 1 in the denominator cancels one of the k plus 1 at the top. So now we have that this is equal to k plus 1 over k plus 2, which is what we're required to prove, that pk plus 1 is equal to k plus 1 over k plus 2. So now what we have is that, so now we can make our final statement that pk plus 1 is true when pk is true. Therefore, Pn, which is the statement, the sum from R is equal to 1 to N of 1 over R into R plus 1 is equal to N over N plus 1 is true for all N, which is an element of the set of natural numbers. So this is what we're asked to prove for 8 using PMI, the principles of mathematical induction, and we have just completed that task. Now let's move on to example 7. In example 7, we're asked to prove by induction that the summation from R is equal to 2 of 2 over R minus 1 times R plus 1 is equal to 3 over 2 minus 2 N plus 1 over N into N plus 1 for values of N greater than or equal to 2. So I'm starting out with the statement that Pn is going to be the statement that the summation from R is equal to 2 of N of 2 over R minus 1, R plus 1 is equal to 3 over 2 minus 2N plus 1 over N into N plus 1. All right, so let's go through the 4 PMI steps. Step 1 is to prove that the statement is true for N is equal to 1. In this case, we're going to prove that the statement is true for N is equal to 2. So P2, we get 2 over 2 minus 1, 2 plus 1. This is the left-hand side. And over the right, we have 3 over 2 minus 2 times 2 plus 1 over 2 times 2 plus 1. So over the left, we have 2 over 1 times 3. Over here, we have, over the right-hand side, we have 3 over 2 minus 5 over 2 times 3. Over here, we have 2 over 3. Over here, the LCM is 2 times 3, which is 6. 2 into 6 is 3. 3 3s are 9. So this is 9 minus 5, which is 4 over 6, or 2 over 3. So the left-hand side and the right-hand side being equal proves that the statement is true for N is equal to 2. So Pn is true for N is equal to 2. Next, we're going to assume that Pk, which is this statement, from r is equal to 2 to k of 2 over r minus 1, r plus 1 is equal to 3 over 2 minus 2k plus 1 over k into k plus 1. We're going to assume that this statement is true. As the second step in PMI, then we are required to prove, this is the third step, that p k plus 1, which is the sum from r is equal to 2 to k plus 1 of 2 over r minus 1 times r plus 1 is equal to 3 over 2 minus 2 times k plus 1 all over k plus 1 times k plus 1 plus 1. Simplifying, we have what? 3 over 2 minus, this is 2k plus 2 plus 1 all over k plus 1, k plus 2, and this is 3 over 2 minus 2k plus 3 all over k plus 1 times k plus 2. So we're required to prove this. Let's change this color ink for that final stage of it. So we're required to prove this. And our starting point is that actually p k plus 1 is actually equal to pk plus the k plus 1 term, the k plus 1 term. So pk, that statement that we assume is 3 over 2 minus 2k plus 1 all over k into k plus 1. Now the k plus 1 term, using the general term, k plus 1 term is 2 over k plus 1 minus 1 times k plus 1 plus 1. So this is actually equal to 3 over 2 minus 2k plus 1 over k into k plus 1 plus 2 over k into k plus 2. So let's just rewrite this a little. Minus and as I said, our job is to prove that this is equal to this. Once we have done that, we're finished with the PMI. The LCM here is k plus 1, k plus 2. So we have 2k plus 1 here minus 2k plus 1. And then we have k plus 2. Let's simplify the numerator of that right-hand side. We have 2k plus 2 minus 2k squared plus 2k plus k is 4k plus k is 5k plus 2. So just working on simplifying the numerator. This is 2k plus 2 minus 2k squared minus 5k minus 2. This becomes minus 2k squared minus 3k, and 2 minus 2 is 0. So we could say that this is just minus k into 2k plus 3. Now putting that back into the solution, we have 3 over 2 minus k, 2k plus 3, all over k into k plus 1, k plus 2. The k's cancel, and this becomes 3 over 2 minus 2k plus 3 over k plus 1, k plus 2. All right, which is what we wanted to prove in the first place, which we just did. So now we've proven this, we can write our final statement that pk plus 1 is true when pk is true. Therefore, Pn, which is this statement, that the summation from what? Is it 2? Yeah. To n of 2 over r, 2 over r minus 1, r plus 1 is equal to 3 over 2 minus 2n plus 1, 2n plus 1 over n into n plus 1. I think that's it. That this statement is true for all n greater than or equal to 2, and n is an element of a set of natural numbers. Example 8. Example 8 is asking us to prove by induction that the sum from r is equal to 1 to n of 3 to the r minus 1 is equal to a half 3n minus 1. So let's start with saying that Pn from r is equal to 1 to n of 3r minus 1, 3 to the n minus 1. So let's test what happens when n is equal to 1. We have P1, the first term is 3 to the 1 minus 1. And that is on the left-hand side. And over the right, we have what? A half into 3 to the 1 minus 1. This is the right-hand side. All right, so let's simplify. To the left, we have 3 to the 0, which is 1. To the right, we have a half. 3 to the 1 minus 1 is 2. And a half of 2 is also what? 1. So now we know that the Pn is true. So Pn is true or n is equal to 1. And that is so because both the left-hand side and the right-hand side came out to be the same. We are to assume that P, K, which is the sum from R is equal to 1 to K of 3R minus 1 is equal to 1 over 2, 3 to the K minus 1. We're to assume that this statement is true. Then we are required to prove that P, K plus 1 from R is equal to 1 to K plus 1 of 3 R minus 1 is equal to 1 over 3, 3 to the K plus 1 minus 1. We're required to prove that this statement is true. All right, I'm wondering if we should simplify over the right. Well, let's not. But here's something that we do know. We do know, let's change the color ink, that PK plus 1 is actually equal to PK plus the K plus 1, the Kth plus 1 term. All right, the PK is summing the series up to K. PK plus 1 is summing the series up to K plus 1. So it's equal to PK, which is the sum of the series from R is equal to 1 to K, plus the Kth plus 1 term. So earlier we assumed that this PK is equal to 1/2, that this statement, we assume this statement to be true, plus the K plus 1 term, which is 3 to the K plus 1 minus 1. So this is 1/2, 3 to the K minus 1 plus 3 to the K. Let's apply what distributive law. So this is 1/2 times 3 to the K minus 1/2 plus 3 to the K. Now, 1/2 3 to the K plus 3 to the K is 1.5 3 to the K, which is 3 over 2 times 3 to the K minus 1/2, which is equal to 1/2 times 3 to the K plus 1 minus 1/2. Factoring out 1/2, we get 1/2 3 to the K plus 1 minus 1, which is what we were asked to prove that PK plus 1 is equal to. So now that we have done that, we can make that final statement that PK plus 1 is true when PK is true. Therefore, Pn, which is the statement, the sum from 1 to n of 3 to the R minus 1 is equal to 1/2 3 to the n minus 1. Therefore, this statement is true for all n, which is an element of a set of natural numbers.